Hello, my name is James. Today I'm going to read some papers. So, once in a while, I will choose some topic that I like, search for the papers that's been written, and read it quickly to get the gist of the papers to absorb the knowledge. A few years back, I met a researcher on deep learning. His name is called Zijin. He's based in New Zealand, and we've been chatting for a very long time about AI technology and anything cool uh, about other technologies as well. So we had the idea of starting up a YouTube channel for reading papers, and this is my first attempt. So here we go. Now the first paper that I'm interested in reading is actually related to my work. I work in Web3. Decentralized technology is what my project does best. And recently, I'm reading a book called Blockchain Consensus. A blockchain project consists of a few things, but I think the most important thing in there is cryptography, which is the underlying technology to ensure the security of crypto tokens and assets. And then there is the blockchain, which ensures that the people in this network and the computers in this network is able to communicate with each other and also achieve consensus. The third part is actually governance. So how do we get people to agree with certain things and go through governance process and make a decision going forward about the project. Blockchain consensus is the topic of making sure that the players in the network, mainly computers, the machines, is able to act as peer-to-peer fashion and being able to trust each other without having to worry about adversaries in the network destroying the network. So in blockchain systems, typically in a permissionless system, you will have any person come in and out, and then in a permissioned network, you will have a group of people that is having control over the network. But regardless of the systems, everyone should be peers to each other. That means anyone is equal. There is no central effort to act as the authority of the network. The analogy is trying to run a bank in a centralized way and then trying to run a bank in a decentralized way. You'll find that centralization is actually easier to build because let's say you have a headquarter in Melbourne, that I am, and then you have some offices in different cities. To be able to keep the database in sync and produce very quick transactions, you can replicate this information in different offices. But Melbourne still becomes the headquarters, so it becomes the master or the main copy, and everyone just have to follow. There's a small, slight propagation delay, but everyone knows how to update their databases according to the state of the um, main server that is based in Melbourne. Now, in the decentralized world, everyone is a peer. So one transaction could come from another location, and then how does everyone trust that the person is doing the right work? This is largely achieved by implementing very clever blockchain consensus mechanisms. And blockchain consensus is not a new topic. Blockchain consensus is built on classical computing, distributed computing consensus concepts. So this book explores everything, but it is written as a textbook. It covers everything, but nothing in depth. And as much as I enjoy reading, learning about all the knowledge, I have to say this book is not very well written for someone like me because I mainly want to read it for pleasure. So in this book, one paper gets mentioned repetitively. So this researcher called Lam Lamport. So over here, Leslie Lamport. He gets mentioned quite a few times because he's the first person, I think, to present this problem and presented the fault tolerance model for the problem. And this problem is Byzantine general problem, which is in the olden days. Imagine without any advanced communication method, a bunch of generals are trying to accomplish some military goals. To send out the message, there are many risks. You can only send out messages to your troops, which are controlled by different commanders, in a very manual way. So sending horses, messages, or sending out actual soldiers as messengers. But then how do you know that the message has been delivered properly and no one tampered with the message? Or if the commanders are talking to each other, how do you know if the commanders are not actually traitors to the army, which might send confusing messages to jeopardize the effort? So Byzantine general problem is the problem in distributed computing because everyone is working standalone. They're receiving messages, they're connected to each other, but there's no real leader in it. Therefore, they can't trust everyone. So they will have to use more information to determine whether the information is true, and determine autonomously whether or not to append some information in their node in order to be able to have the most right information recorded in their computer. So blockchain system requires this heavily. So from there, I started searching for Leslie Lamport's publishment or publishes. So one of the first one that I was able to find is actual website. So it seems to be hosted for Lamport or by Lamport himself, and it's been updated kind of half a year ago, and I can find the history of his content. So I did a little bit of search and found the Byzantine general and transaction commit protocols. Transactions and commit are two things that I've heard at work quite frequently, so it'll be interesting to read this paper. And then I want to find the original sort of definition of the problem in his sea of papers. That is the Byzantine general problem. So I've got these two loaded up. We're gonna take a look. So let me load this one up as well. PDF. Yep. Good. And Byzantine general problem is here, and then the PDF is here. So BYZ problem. Let's take a look. The Byzantine general problem. I already understand Byzantine general, what these two are, and so I understand the title pretty much fully. There are a few researchers. Because this research is quite old, I think the people who are involved in this must have done quite well. But let me try to kind of search these people a bit and see if I can find any information about them. Researcher. He has a Wikipedia page. Byzantine fault tolerance. Yeah, seems to me he has done quite a bit in this field. Filed many patents. Okay, so that's very trustworthy. Marshall, please. Marshall, peace. See ACM Digital Labs. That's just got his page in there. So seems to me he's not very active anymore. He doesn't have an online presence, but that's okay. So we already know these two, and it's good enough to continue. Reliable computer systems must handle malfunction and give conflicting information between parts of the system. Situation can be expressed in a group of general Byzantine army camped with their troops around enemy cities. Communication by messengers. The generals must agree upon a battle plan. However, one or more of them may be traitors who will try to confuse each other. So this problem is to find an algorithm to ensure that the loyal generals will reach agreement. So as long as royal generals are able to reach agreement, then we can call that a consensus. It's showing that with you only using oral messages, this problem is solvable, and is only more than 2/3 of the general are loyal. So this is important. As long as 2/3 of the generals are loyal, are saying the right things, doing the right things, then we can solve this problem. If lower than that amount is present in the network, then we can't solve this problem. So we basically cannot achieve consensus. So a single traitor can be confounded into two loyal systems, which forgettable written messages. The problem is to solve for any member of generals, possible traitors. Application of solutions to reliable computer systems are discussed. I'll skip the introduction. Zijin actually showed me some tricks about scientific writing. It's actually very important to look at the figures that the research offers. The figures can tell you a lot and save you a lot of time in reading. So looking at figure 1, Lieutenant 2 is a traitor, so we have commander seems to be issuing attack instead of a retreat command, and Lieutenant 2 is not loyal. He's at retreat. And then there's a scenario that commander can become also a traitor. So the commander could be giving confusing commands to lieutenants. I suppose they can work out that the commander is a traitor and decide to not action on it. Wow, this is scanned copy, so it must have been pretty old. Command lieutenant. So this is having 3 lieutenant and 1 commander. Let me make this smaller. And okay, I can do this. And then figure 4 says the commander algorithm OM is the algorithm OM. The commander is a traitor, and there are different channels for these 3 lieutenants to work out what's going on. Okay, good. Let's keep scanning. Figure graph. I want to see what these figures are. These captions are not really good because it doesn't really explain what this is trying to say. Then I need to scan the vicinity of this figure to make sense of this. So far, assume that general send messages directly to other general. However, we now remove this assumption. Instead, we suppose that physical barriers place some restrictions on who can send message to whom. We consider these generals to and from nodes of simple finite undirected graph, where an arc between the 2 nodes indicates that these 2 generals can send messages directly to each other. Okay. So there seems to be 2 algorithms, OM and SM. Let's come back to that a little bit later and see if there are more figures for us to understand. No, that's it. So my next interest is finding out this OM algorithm. Alright, so this article is a bit old. Doesn't seem to allow me to find text. Oh, okay. So it is searchable. So there are words here, but why can't I find it? Why can't I find the OM definition? OM algorithm. Okay, oral message algorithm. So oral message. What does oral message mean? We inductively define oral message algorithm for all non-negative integers m by which a commander sends an order of n-1 lieutenants. We show that OM oral message solves Byzantine problem for 3m plus 1 or more general. The algorithm assumes a function majority with the property that is majority is a value vi, blah blah blah, a lot of math stuff, and I think this is good. The following algorithm requires only aforementioned property of majority. The commander sends his value to every lieutenant. Each lieutenant uses value received from the commander or uses the value retreat if they receive no value, if he receives no value. The commander sends his value to every lieutenant. So when m equals 1. So this is when you have nothing. Okay, I don't quite understand this part. To understand how this algorithm works, consider that the case m equals to 1, n equals to 4, figure 3. Figure 3. Yep, okay. x. So, okay. So guess for Lieutenant 2, just work out the majority. Lieutenant 1, yeah, okay, I see. Yeah, so Lieutenant 2 is able to use numbers to be able to figure it out. And then for figure 4, you just count the number of commands. So commander is a traitor, right? So X is probably wrong. And then he sends X, but he receives Y, and then X and Z in it. So receives Y and Z. So they're all confusing, which then if you use the majority rule, it's unresolved for Lieutenant 2, Lieutenant 2 for Lieutenant 1, and for Lieutenant 2 it receives Y from commander, receives X from Lieutenant 1, and then receives Z from Lieutenant 3. So this is unresolved either, so it won't action actually. For the third one, Z, Y, and X, so it's the same. So I see how this solves the problem. And then what is the AM? AM algorithm. So OM, oral message. I'm scanning for AM, the definition of AM. SM, sorry. It was actually supposed to be called SM. So now we extend SM. So SM1. Signed messages. Okay. A solution with signed messages. So in cryptography, you can have a message signed by someone which other people can verify whether that is indeed coming from the other person. So this is more relevant to my field, because if you can sign, if you can provide a signature, then you know that this indeed comes from that person. So a loyal general signature cannot be forged. These are assumptions, which is important. Any alteration of the content of the signed message can be detected. Anyone can verify authenticity of general's signature. So this is trying to investigate whether there's an algorithm that works if the messages are signed. So let's take a look at this figure. The commander is a traitor. We know that commander signs it. It's receiving attack but receiving retreat from here, so this doesn't resolve. So scanning through, I'm trying to read it quickly without spending too much time on it. If there are at least at most m traitors. Okay, so that's different than the previous one, the unsigned one. So SM is able to solve the Byzantine general problem if there are at least m traitors, at most m traitors. So it has a higher number of tolerance than the non-signed one. Okay, so there's something talking about reliable systems, probably talking about its faults, and let's read the ending conclusion. Achieving reliability in the face of arbitrary malfunctioning is a difficult problem, and its solution seems to be inherently expensive. The only way to reduce costs is to make assumptions about type of failure that may occur. Okay. For example, if often assume that computer may fail to respond and never respond incorrectly. However, the extreme high reliability is required. Such an assumption cannot be made, and the full expense of a Byzantine general solution is required. Okay, so I think we're done with this paper. Let me move to this one for a really brief read. Byzantine general and transaction commit protocol. By looking at this, I think this transaction commit protocol is a solution to Byzantine general problem mentioned in the Byzantine general problem paper. And let's confirm this with the first sentence. The transaction commit problem is a distributed database system in an instance of weak Byzantine general problem, which is showing that even under the assumption that a process will fail only by failing to send any more messages. A solution to this problem that can tolerate k failures must, in another worst case, require at least k+1 message passing delays. Under this same assumption, a simple solution that exhibits the optimal worst case behavior is given. So it is indeed trying to solve some problem, and the problem is called weak Byzantine general. Weak Byzantine general is probably not defined in the other paper. Nope. There are only 2 references of weak. So I would like to understand what the weak Byzantine general problem is. Okay, so we will show that design fault tolerance protocol for arriving this decision equivalent at the weak general problem introducing 7. Where is 7? This is quite a long paper. Lamport, the weak Byzantine general problem, Journal of ACM. Weak general problems. So I should have all the Lamport researchers over here, and weak Byzantine general problem is here. Let's just read the abstract of it. The weak general requires processes to reach agreement upon even value, even some of them may fail. It is weakened by allowing them to agree upon a incorrect value. If failure occurs, the transaction commit problem for a distributed database is a special case of weaker problem. It is shown that, like the original Byzantine general problem, the weak version can be solved only if fewer than 1/3 of the process may fail. Unlike the original problem, approximate solution exists that can tolerate arbitrarily many failures. Byzantine general problem is defined here. And the weak what does weak mean? So if we allow some faults to occur, like the consensus faults to occur, then it's called a weak Byzantine general problem. Let's just understand it this way, and feel free to correct me if you know otherwise. So going back, so there is no lots of math formulas which are important. There are no figures in this paper, which is going to be a little bit hard to read. So introduction, the weak Byzantine problem, explanation is here, time complexity of this. I guess time complexity is the cost of transferring messages to each other. There are many things here, and then theorem 2, algorithm BG satisfies. So I won't be able to draw any meaningful conclusions from this paper because it seems to be a question, challenge, or theory proof kind of paper. I'm not interested in the proof, I'm interested in the essence of the solution, how that solves it. But I guess it's something to do with and how exactly this transaction commit protocol works. I guess that's probably just in the first few paragraphs. Since the work on Byzantine general problem has concentrated on handling lying processes, there seems to be a general feeling that this work is not relevant when the process fails only by crashing. Okay. So it seems like this solution is assuming crashes and not focusing on lying or wrong messages being sent, which is more realistic because the crashing happens a lot more often than attacks. So I'm gonna stop here and record the next section, which is on a different paper on consciousness.